Once again, CERN has made news. Our picture of the universe may change as a result of an astonishing discovery made by the renowned particle physics laboratory's Large Hadron Collider. These unusual results may indicate the presence of extraterrestrial life in a parallel reality, according to scientists. We'll talk about the recently revealed CERN revelation that alters everything in this video. Finding: the terrifying discovery. Scientists at CERN observed an oddity with a certain type of quark in a recent experiment using the Large Hadron Collider. There are various kinds of quarks, which are the fundamental units of all matter. These various varieties are referred to as flavors by physicists. Some of these so-called quark flavors degraded quickly and were quite unstable. The beauty quark, which has an average lifetime of 1.5 trillionths of a second, was the focus of this specific abnormality. The quark's decay pattern was found to be drastically different from what scientists had anticipated using the Standard Model. According to the Standard Model, which predicts a 50-50 possibility for both particles, a beauty quark should decay under the influence of the weak force and change into leptons, a group of lighter particles, either an electron or a muon. The Large Hadron Collider data, however, revealed something comparatively different. According to the findings, these quarks only decayed into muons 70% of the time, compared to electrons. Since electrons and muons are carbon duplicates of one another, the only distinction being that the muon is 200 times heavier, this was particularly noteworthy. However, the rate of transformations shouldn't be impacted. Since the beauty quarks decay through the weak force, both particles should undergo the transformation the same amount of times. This is because all the forces in the Standard Model are supposed to pull on these two particles with equal strength. A novel particle type that has never been observed before entering the process is the only way this anomaly may happen. It has led some scientists to hypothesize that a novel form of physics might be involved. New physics should result from a new force-carrying particle, which could broaden the scope of the Standard Model and provide answers to numerous unsolved problems. The new physics. The potential for novel physics. Since there are currently few methods for investigating particles, the Standard Model hypothesis provides the best explanation for the behavior of the bizarre world of particles. Everything we know about the fundamental components of the physical world is precisely described by the Standard Model, a scientific framework. The startling thing is that physicists are well aware that this model is not yet complete and that there are still many parts to be put to the puzzle of reality, despite its comparatively high level of accuracy. Only three of the fundamental forces, the electromagnetic force, the strong force, and the weak force, can be described by the Standard Model. It currently lacks an explanation for dark matter, the predominant form of matter in the cosmos, as well as a description of the force of gravity. Researchers discovered an abnormality in the data they were reviewing during recent trials that did not match what is known within the standard paradigm. This time, however, something has attracted the interest of scientists, and they recognized that they needed to take a deeper look to distinguish this new occurrence, even though it is normally not rare to uncover outcomes outside of this paradigm with the enormous volume of data that the LHC gives out. Could this force be something new? The researchers have thought that a new fundamental particle, which they have named Z', a force-carrying particle, might exist in order to explain this extraordinary discovery. According to the researchers, this force would interact differently with electrons and muons, but the extent of its interactions with the particles of the Standard Model is still unknown. This is despite the fact that it is most likely very weak because there have been no indications of it up to this point. The discovery of new force-carrying particles would be a breakthrough that physics has been waiting decades for. If this discovery is verified, physicists hope it will assist solve long-standing puzzles about the cosmos and provide answers to long-standing queries like what dark matter is and how the Higgs boson contributed to the creation of our world. According to a notion developed by some scientists, this unidentified force could contribute to the unification of the fundamental forces of existence, which has been one of physics' main objectives for the past century. The Huge Collider of Hadron. Since its founding in the middle of the 1950s, the European Council for Nuclear Research, or CERN, has been conducting incredible experiments. For both positive and negative causes, they have been in the news a lot. People's reactions to the various trials they have conducted have been conflicted. Given the magnitude of the organization's funding and the nature of their research, some of their experiments have raised concerns about the potential development of black holes, rips in our reality, and a variety of other hypotheses. Out of all their experiments, the construction of the Large Hadron Collider stands out as one of their most well-known and contentious accomplishments to this day. The world's largest particle accelerator, the Large Hadron Collider, is more than 27 kilometers in circumference and costs more than $4.50 billion. That sum of money is enormous. Even so, a lot of people who are in favor of CERN's investigations would contend that the money was well spent because the LHC has produced some of the most groundbreaking discoveries in recent decades since it was built. The Higgs boson, which oddly is also known as the God particle, and numerous other particles that were previously unknown before being discovered by the LHC are examples of such startling discoveries. A variety of particles can be accelerated around and around the loop by this enormous LHC. This continues until the particles complete more than 11,000 laps per second and approach the speed of light. How did they accomplish this? They achieved this by generating a magnetic field inside the accelerator using incredibly strong electromagnetics. The strength of this magnetic field is over 100,000 times that of the Earth's surrounding magnetic field. However, not everyone is a fan of science, particularly not science that seems as contentious as the CERN experiments. Some have expressed concern about how producing a magnetic field of this strength may affect nearby devices and possibly the Earth's magnetic field. I hope it doesn't destroy it. The particles moving in opposite directions are compelled to collide with one another when these particles reach their maximum speed, which is 91.91% the speed of light. This powerful collision releases a variety of particles and a great deal of energy. The LHC was constructed with the capacity to accelerate a wide range of particles. Researchers will be able to observe various particles emerging following the hits thanks to this. What is Elon Musk saying? Musk claims that CERN built the Large Hadron Collider, the biggest and most powerful particle collider in human history, between 1998 and 2008. More than 10,000 scientists, hundreds of universities, and laboratories from more than 100 nations helped with this procedure. It is situated inside a 27-kilometer-long tunnel. Near Geneva, the French-Swiss border is located approximately 175 meters below the surface. In addition to being almost 4 times more powerful than the previous world record, the first collision ever recorded in the Large Hadron Collider had an energy of 3.5 tera-electron volts per beam. The energy reached 6.5 tera-electron volts per beam once the LHC was further improved. According to Musk, the Large Hadron Collider is ideally suited for proton beam collisions. Furthermore, it has the ability to accelerate heavy ion beams, particularly lead ions. Collisions between protons and leads often occur once a year. Allowing physicists to test the predictions of numerous particle physics theories is the main goal of the Large Hadron Collider. Notably, they are measuring the Higgs boson's characteristics and searching for the vast family of new particles anticipated by subatomic particle theories. An explosion of particles. These particles have a brief lifespan, and when they finally collide, a shower of particles will shoot out in all directions. Before vanishing into oblivion, the majority of them remain in existence for a nanosecond or less. Researchers can find new particles in these flurries by changing the kinds of particles present. Supersensitive detectors are positioned around the collision sites with the aid of specially created technology to ensure that no information is lost from any accident. However, sorting through the vast amount of data that is generated takes a great deal of time and labor. Every year, the LHC's experiments can produce over 15 petabytes of raw data from these collisions, which the researchers painstakingly sort through to find the information they need. In 2017, researchers permanently added more than 200 petabytes of data to the LHC's tape libraries, marking a major milestone. 1 petabyte of data is equivalent to almost 2.5 million movies, to put this enormous volume of data into perspective. The boson of Higgs. It is claimed that the Higgs boson is an elementary particle connected to the Higgs field. It is this field's quantum excitation, which is comparable to how you observe water waves. The boson itself resembles a brand new species of animal in the menagerie of particles. It lacks the carriers of quantum interactions like weak forces, electromagnetic forces, and nuclear interactions, as well as the quantum characteristics of elementary matter. The two massive multifunctional experiments ATLAS and CMS simultaneously made the groundbreaking discovery of the Higgs boson at the Large Hadron Collider. It was revealed at CERN on July 4, 2012. At that time, the new scalar boson was primarily detected in two uncommon decay channels that provided the cleanest signal: the direct decay in a pair of Z bosons, the carrier of the neutral weak interaction, and the decay in a pair of photons, which included a purely quantum virtual process. Even though the standard model was finished at the time of the Higgs boson's discovery, research into this elusive particle continued. Confirmation of the Higgs decay was one of the major findings made since 2012. At the time, CERN stated that the third run of the LHC would deepen the study of this elusive particle, especially once the high-luminosity upgrade of the particle accelerator is finished in 2029. Researchers will have greater chances to observe unusual physics, such as occurrences beyond the standard model, as a result of the LHC being able to perform more collisions. According to CERN's estimates, 15 million of these particles will be produced year as the accelerator is updated. In contrast, the LHC produced 3 million Higgs bosons in 2017. This could be crucial for identifying more Higgs boson flavors. Up to 5 other Higgs boson types are predicted by theories that deviate from the standard model of particle physics. These types may be produced less frequently than the fundamental Higgs boson. Strong evidence of a magnetic Higgs boson has already been shown by scientists prior to the improvements. The Higgs boson is known as the God particle for a reason. Popular media helped to solidify the Higgs boson's nickname as the God particle following its discovery. The Nobel Prize-winning physicist Leon Lederman is typically credited with starting this, having referred to the Higgs boson as the goddamn particle in exasperation due to its difficulty in detection. When Lederman wrote a book on the Higgs boson in the 1990s, he wanted the title to be The Goddamn Particle, but the publishers changed it to The God Particle. This marked the start of a problematic relationship between the particle and religion that still irritates physicists today, according to Business Insider. Since only particles would have mass with this feature of nature, it is difficult to overestimate the significance of the Higgs boson and the Higgs field. This may help to explain its exaggerated moniker because it implies that there would be no stars, planets, or people. Just why research the Higgs boson? Scientists continue to research the Higgs boson for two key reasons, aside from the obvious need to carry out the most accurate characterization of the new particle. Their first goal is to comprehend how the early cosmos produced the physical vacuum in which we dwell. Second, they are trying to figure out how to stabilize this physical vacuum. The Higgs field is special because it gives the physical vacuum a mean anticipated potential energy that is not zero. To put it simply, this is what really makes our universe different. The shape of the energy potential, which is thought to be the cause of the weak force working at extremely short ranges and the electromagnetic force with unlimited range, may be accessible, according to scientists. Scientists must investigate the interactions between the Higgs bosons in order to accomplish this. They must create pairs of Higgs bosons in order to accomplish this. The crucial question of where the mass of all other elementary particles came from was resolved in part by the Higgs boson. Its mass, however, has not yet been determined. Any theoretical symmetry introduces unwelcome instability and does not shield this mass. So much so that quantum fluctuations could disrupt the physical vacuum itself through quantum processes. Scientists are still searching for more Higgs boson-like particles that would indicate the presence of the new physics required to stabilize the Higgs boson mass, but fortunately, this is on timescales, which are significantly larger than the known lifetime of the universe. All of these considerations encourage access to higher collider energy and, if feasible, the analysis of considerably more data. For this reason, 10 years later, thousands of scientists around the world remain committed to the work. Why did the Higgs boson take so long to discover? The Higgs boson was discovered in 2012 after being postulated in 1964. Why it took so long has been questioned by science enthusiasts. This is due to the Higgs boson's extraordinary instability and weight. The scientists had to concentrate a significant amount of energy in a compact volume in order to create such a hefty particle. A high-energy collider was required. Only a small portion of the Higgs particles can be separated from the common background due to their diverse decay patterns after production. To find these particles, scientists built the biggest and most intricate detectors. They then extracted a Higgs boson signal by analyzing hundreds of billions of proton-proton collision events. Is it possible that CERN unlocked a dimensional portal? Will CERN's initiatives and findings enable us to make audacious discoveries? Or is it going to lead us to our final end? There are three widely accepted views among conspiracy theorists as to what CERN is actually doing. The first and most terrifying hypothesis, which led to accusations against CERN, is that the organization is attempting to open a portal to hell. According to some, we will pass the gates of the ultimate inferno as a result of CERN's manipulation of subatomic particles moving at the speed of light. But CERN has made it clear that the purpose of developing antimatter is to improve our understanding of mass and matter. Subatomic particles with the opposite electrical charge of matter are referred to as antimatter in the Wikipedia. Proponents of the Big Bang theory believe that antimatter should be treated equally with matter because it was formed during the universe's birth. Conversely, antimatter is extremely uncommon. The Mandela effect is the second conspiracy hypothesis involving CERN. The Mandela effect is only a phenomenon when a large number of people recall a prior event in a different way than it actually happened. According to some conspiracy theorists, the particle experiments at CERN will probably induce changes in reality and transport our world into an other dimension, resulting in a massive Mandela effect. Third and last, some conspiracy theorists think that the CERN complex is the actual location of human sacrifice. According to a purported 2016 internet video, ritual sacrifices were taking place at CERN. Several shrouded persons were allegedly seen strolling around the CERN grounds in the video. There were rumors that the video showed the cloaked people stabbing a little girl in the chest. The Guardian claims that a CERN representative at the time stepped forward to refute the allegation, claiming that the ceremony was a part of a complex practical joke. There is still no answer to the question of whether a police inquiry was conducted after that. The fact that conspiracy theories have long targeted CERN is not new. Therefore, it should come as no surprise that conspiracy theories would surface online on July 5, 2022, when scientists returned to work after 3 years of renovations and maintenance. This announcement may disappoint scientific enthusiasts, but it is obvious that CERN has no intention of opening a doorway to the future, hell, or any other dimension. Found ghost particles. More than 300 feet underground, protons continue to fly around the 27-kilometer circle of the largest particle accelerator in the world. Its capacity to collide particles at extraordinarily high energies has been allowing humanity to explore the uncharted physics frontiers for more than 10 years. The LHC's Forward Search Experiment Detector, phaser, has accomplished an unanticipated objective. It detected 153 events that were neutrino interactions with very high certainty, detecting high-energy neutrinos produced by a particle collider for the first time. Scientists may be able to learn more about the universe's highly intense neutrino interactions and the mechanisms by which stars burn and burst as supernovas thanks to this important advancement in particle physics. Small subatomic particles called neutrinos are present practically everywhere. Neutrinos are created whenever atomic nuclei unite or separate. Cosmological rays and radioactive decay in particle accelerators and nuclear reactors on Earth as well as the inherent radioactivity of potassium in bananas, are the sources of these. But these particles are the ultimate cosmic ghost. Once created, they seldom ever interact with matter. They are massless and chargeless. Every second, over 100 billion neutrinos travel through every square centimeter of our body, but they are so invisible that we are unable to sense them. Since they were first observed bouncing off a nuclear reactor in 1956, scientists have been pursuing these elusive particles, which have been dubbed ghost particles. In 2021, physicists discovered the signs of 6 neutrinos, but it took them 2 whole years to gather enough evidence to prove that these spectral particles were real. The ghost particles can tell us about deep space in ways we can't learn otherwise, said James Boyd, a CERN particle scientist and co-spokesperson for Phaser. The LHC's extremely high-energy neutrinos are essential for comprehending fascinating particle astrophysics discoveries. Data collection for the experiment will continue through the end of 2025. Researchers anticipate discovering more of these ghost neutrinos and revealing physics' hidden complexities. Can earthquakes be caused by the Large Hadron Collider? Tectonic plate movement is the cause of earthquakes, which are natural risks. At their borders, like the center of the Atlantic Ocean or the Pacific Rim, these plates can lock up and accumulate tensions as they travel in different directions or even past one another. This stress is experienced when the plates abruptly separate. Alleviated, which results in a massive energy release that triggers an earthquake. Earthquakes cannot be caused by the LHC. Every year, millions of earthquakes occur all across the planet, but the majority are too tiny to be picked up without monitoring technology. There is no connection between the operation of the LHC and earthquakes, nor is there any way that the LHC may cause earthquakes. Because of their extreme sensitivity to minute motions, several high-precision devices at CERN are able to detect earthquakes. There are about 100 hydrostatic leveling sensors in the LHC. These sensors track the movements of the magnets that guide particle beams around the 27-kilometer ring of the LHC. After traveling through the Earth, these sensors are able to pick up the vibrations that distant earthquakes release. Another instrument for measuring subterranean structure movements that may have an impact on the exact placement of the particle detectors at the LHC is the precision laser inclinometer. They can also detect earthquakes because of their sensitivity. CERN and its objective. Founded in 1952 as a provisional body, CERN stands for the French, Conseil Européen pour la Recherche Nucléaire, or European Council for Nuclear Research. Its duties include creating a top-tier fundamental physics research organization in Europe. We now have a broader understanding of matter because, at the beginning, pure physics research focused on comprehending the interior of the atom, hence the term nuclear. Particle physics is the primary field of study at CERN, and it reaches far deeper than the nucleus. Because of this, the CERN facility is frequently referred to as the European Laboratory for Particle Physics. The study of the basic components of matter and the forces that exist between them is known as particle physics. The biggest and most sophisticated scientific instruments in the world are used by the researchers at CERN. These are used to investigate the fundamental components of matter. By exploring the smallest components of our universe, we want to expand the limits of human knowledge. What will the next discovery from CERN signify for science going forward? How do you feel about these findings? Do you believe they might have an impact on us? Tell us in the comments section. I appreciate you watching. To view more videos, don't forget to like and subscribe.